Yes. So, so it's great to be back here, and so I'm going to talk about physical zero-knowledge proofs and nuclear disarmament. This is joint work with Alex Glaser, who's right here from the Princeton Woodrow Wilson School of Engineering, and with Robert Goldston from the Princeton Plasma Laboratory. And I should warn you that this talk will be very light on math, very simple math, but I hope Amir will compensate for that with some heavy group theory in his talk in the afternoon. Okay, so typically what we do in cryptography, you can think of it like at least the classical things that people have done in cryptography is find digital analogs to what we can do in the physical world. So we could lock something inside the box, and then open it with a key, and that's with the digital analog of that is encryption. A commitment scheme, you want to place a sealed bid in an auction, you use digital commitment. You want to sign, authenticate a letter, we convert it to digital signature. So that's kind of like classically what you do in cryptography. And today we're kind of talking about the reverse direction. We're taking something that exists in the digital world, zero-knowledge proofs, and we find the physical analog of the same thing. And there are not too many works about that. There are people who use kind of physical things in cryptography. People use cryptography intuition to break locks, actually, and some of the most similar thing to what we're doing is the zero-knowledge protocol for Where is Waldo, which is a very nice paper if you haven't read it, published in the prestigious Journal of Cryptology, and look it up. And
there are some papers, both Georgian for oblivious circuit evaluation using physical envelopes, and then Silvio.
Yes, for auctions with like some.
Envelopes in envelopes.
Yes.
Physical.
Yes. So I guess there are like other things where they kind of they do kind of reverse things, and so okay. So zero knowledge proofs. I guess for most of this audience familiar, but let's just say what they are. So you basically have two parties. Usually they call Alice and Bob. I'll call them Anna and Bob because I want one of them to be Russian and the other American. And Anna wants to prove to Bob that some statement is true, but doesn't want to reveal why this thing is true. And some canonical examples that are used in these things, like say, you want to prove the two graphs are isomorphic without giving away the isomorphism. So this is Goldreich, Mikhaili, Wigderson. And what's more similar to what people use in, like people actually use zero-knowledge proofs is they want to prove that some string is a valid encryption of a message, and maybe a message satisfying some properties. And this thing, like, there is something paradoxical about it, and I guess when people first came up with it, it seemed like maybe a very unique and bizarre phenomena that applies only to very particular cases. But then Goldston, Mikhaili, and Wigderson show that basically every statement can be proved. If you can prove it, you can actually prove it with zero knowledge. And now it's very, very much used. So efficient variants of so people have been looking at statements of this form and for particular encryption schemes and particular statements, proving them very efficiently, and that's used all over the place in lots of cryptographic applications. But for us, what we need is just, this is what zero knowledge is. You want to prove a statement, prove that a statement is true without revealing why it's true, and cryptography tells you that actually, in principle, this is possible. So, nuclear disarmament. So generally, I think it's probably not very controversial to say that we would like the world to have fewer nuclear weapons than it has today. And in fact, like it's basically agreed, say, both the Americans and the Russians actually agreed that they have more nuclear weapons than they want, and they would both like to move to an equilibrium with much fewer, maybe zero, but much fewer than what they have right now. And indeed, one of the pillars of the non-proliferation part of it is that countries that didn't have nuclear weapons will not acquire them, and the other part is that countries that do have nuclear weapons will work toward nuclear disarmament. And right now, the US and Russia account for about 95% of total nuclear weapons in the world. And so far, the treaties between them have limited the number of deployed weapons, and not the total number of weapons, but it's clear that the future treaties will talk about limiting the total number of nuclear weapons and eventually reducing them to much lower levels than what they have right now. The way, Alex, feel free, if I'm saying something completely wrong, feel free to correct me. And what you require if you want to do that is verified warhead dismantlement. You want to actually not just not deploy the warheads, but you actually want to destroy them. And you really need to verify. So, I mean, the sentence, Reagan coined a sentence, trust but verify in the context of nuclear treaties. And you really want to make sure that no one cheats. And instead of, they say that they destroyed the nuclear warhead, but they actually kept some of the plutonium for themselves, or they destroyed an old warhead and they kept the new good ones around, or they destroyed the fake warhead, they destroyed the coffee machine and told you it's a warhead. So you really want to make sure that no one cheats. And it's actually pretty important because in some sense, you really want to, right now the US and Russia is about parity. Each has about, 10,000 weapons. If they went and reduced the number of weapons to, 500, but Russia cheated and they still have 1,000, that could seriously alter the balance of power because it might actually be the case that the Russians might be able to, strike the 500 and still have a capability, the whole kind of equilibrium might be spoiled. So as you reduce significantly the number of warheads, you really want to make sure that this actually happened. And so of course, treaties always involve some political challenges, but there is also like a technical challenge, and this is that as part of that, you need to verify that the warhead that a country says we're going to dismantle is actually authentic. But you really don't want to reveal, I don't know, it might be surprising, but it turns out that nuclear warheads are very classified objects and their design is not public information, and you really don't want to reveal the design. You don't want to let the other country open it up and examine every part of it and all that. You don't want to know what technology you have. You don't want to know what design you're using, its limitation, its strengths. You could copy from it. So this is basically the technical part that we're interested in this talk.
Is this it's really secret?
What?
Is it really secret?
Yes. Yes, Alex can say. Yes. Like basic facts about even exactly how much, say, plutonium is in the warhead is secret.
And you Google it, you won't find the secret design somewhere?
And you might find CIA at your door.
I mean, you can think of several motivations for it. Like if you, one theory is that these things, most of them have never been tested. You're afraid that if the other side sees your design, they might realize that it doesn't work. So
how do you know the number? I mean, that's going to, why is there even a reason to think that there is 10,000 either in the US or because they both may agree to reduce it to zero or destroying 10,000 and keep another 5.
So they have, so I think there is a very complex issues around disarmament and very complex protocols. So it has many components. So part of the components are declarations that have been going on for a long time, where every country declared how many warheads they exactly have, and there is nuclear archaeology where you go to the sites where they produce the weapons, and you could kind of try to recover how much they've produced over the years, and maybe Alex can add.
But I would only maybe say, I mean, as you mentioned, right now the US and Russia has both 1,500 deployed strategic nuclear weapons, but there are 10,000 in the dismantlement queue, and no one really cares about them because you have 1,500 deployed, and you don't worry about all these warheads in storage. But if you go to lower numbers, and people talk about several hundred, there was a news item only, I guess, a week ago that the Pentagon is looking at different options, going to 300, 800, or 1,100. At some point, these weapons in the basement, they will become factors in these calculations. And at that point, you would start having these discussions. Do we want to verify dismantlement of these weapons?
No, but even the deployed one, it's clear how many are deployed. I mean,
yes.
Yeah.
We even share GPS coordinates. We're basically not counting weapons. We're counting the missiles. And
Yeah.
we know there's a missile silo, and there are only 3 warheads on that missile. That's what we count. It's much harder to count a warhead that's sitting somewhere in a room, or which you may not know about, so to speak.
So, but anyway, this is just one component, I guess, in a complex process which will have lots of checks and other checks to make sure that people are not cheating. But at some point, you need to do this as well. And people have been aware for a long time that this is.
And maybe it's also worth mentioning. I mean, every year the Russians and the US are dismantling hundreds, sometimes thousands nuclear weapons. It's just not verified. And the assumption is one day, I would argue it's likely that we would say, well, we'd like to actually verify this process. And this is actually an idea that goes back to the 1960s, when the US first proposed 60 tons of weapon-grade uranium to be transferred for peaceful purposes. That was right after the Cuban Missile Crisis. Very surprising. And the Soviets said, thank you very much, we're not interested. How do we know you're actually dismantling nuclear weapons? And the US said, well, we're going to demonstrate it to you. And this was the first time in 1965 or so that the US actually looked into that problem. Can we demonstrate to the Russians or the Soviets that we're destroying nuclear weapons without telling them how they look like? Very primitive compared to what Boaz will, I guess, talk about today.
I guess people can, maybe people will think this is also primitive, but so yeah, and one example for why these things are like delicate is as part of these kind of like mutual trust things, the Soviet at some point let the US take a gamma ray spectrum of a cruise missile. Their idea was, that you couldn't learn the design by looking at this graph, but they were wrong, and they regretted it later. And the reason they were wrong is that, in principle, it is what's called auxiliary information in cryptography. In principle, yes, you couldn't recover a design just looking at this information, but if you had a list of, 10,000 alternative designs that you think the Soviets might have had, and you ran all of them in a computer and try to match to see what would have a gamma spectrum of these would look like, then you would be able to match this thing. And in some sense, you see that. In some sense, so that gives rise to this intuition that. In some sense, it's a very problematic thing. If you're trying to measure something and you're going to get.
What I'm not saying is why is the design of the nuclear part so important? It just blows up stuff, right? Probably the important stuff is more the guidance system, and so you get the pinpoint accuracy.
So maybe Alex can answer this question.
Well, there are many reasons. I'm not defending the argument, but I mean, one reason is you may be surprised how little material you need, and we know you need at least 4 kilograms of plutonium, but in fact you may need much less, and the weapon states are not willing to tell you just how much less. The second very important point is you can actually learn something about the vulnerability of the design. You may learn how to defeat the weapon. Say you have an incoming missile that's heading to your country. You may know if I shoot down another missile and generate a neutron pulse in space, I might actually disable this warhead. And you may, that's actually true. There's some, we did figure out a few things about defects in nuclear weapons that way. You may learn from such a spectrum that the Russians actually have a problem with their design. We can disable their weapons before they impact in the US. just by looking at that spectrum.
I see.
So, I mean, some people are pretty paranoid about, weapon design issues.
I see. So this disabling would involve launching another missile to intercept it and doing some kind of nuclear reaction right there.
Right.
Is it going to get more cheerful?
Yes.
You could reveal that the design incorporates some kind of rare substance, and then, talk whoever corner of the market in that substance, so they can't build new ones.
Yes,
That's right.
yes, so, yeah, in any case, in some sense, even if it's not justified, which it probably is, the mere fact that countries are paranoid about this design information means that if we want to progress, we have to find a way for them to verify without revealing it, even if they should reveal it, and it shouldn't be a secret. So what's the approach? So people have been aware of this problem, and what's the approach that they've been using? It's called the information barrier approach. So this is the idea. You put the warhead inside some big iron box, or some box, let's say iron, and you have inside some basically robot that and computer-controlled measurement apparatus that measures this warhead, and at the end it just gives out either a green light or a red light. A green light said yes, this is an authentic nuclear warhead, and a red light says no. And the idea would be that the party that inspects only learns if the light was green or red, so it didn't learn anything about the design. And this is just an example of like some machine like that people have built. And I don't know if you can see here, but they are actually like the text here is both, the labels are both in Russian and in English, so it will be fair to both parties. And these are the things that, like in joint work with US and Russia, people have developed these technologies. And the main issue is that you have this very complicated machine, and you want to verify two properties. So one property is that you cannot spoof it. You cannot put inside the coffee maker, or more realistically, a weapon where you replace the military-grade plutonium with lower quality plutonium or something like that, and it will still output a green light. And the second thing is it does not leak more information than intended. Maybe the grid lights, if you actually look at it, it actually blinks in Morse code the secret design information. And you can't blame people for being paranoid, like exactly like, for example, what the Americans did to the Russians with the Spectrum thing is exactly that. They had a machine that wasn't supposed to leak the information, and they did extract information from it. So, in the language of the nuclear disarmament community, the first property is called authentication. The second one is called certification. And yeah, and that's the challenge here. Like you have this complicated machine that, and you have to make sure that no one inserted any kind of trapdoor into it or some deliberate weakness or indeliberate.
And they call the missile Artu?
Artu? Artu Merlin. So the intuition, behind the need for information barrier is this intuition that we had before. Like if the measurement is useful to verify the word, it must contain the sensitive information, and therefore it needs to be protected in an information barrier. And we can see that actually zero-knowledge proofs really challenge this intuition. They say that sometimes you can somehow prove that the thing is authentic without revealing any information. So it's not so this kind of common wisdom in that community that it must be the case that if whatever measurement is useful to verify authenticity is also must leak information is not necessarily correct.
It's also destroyed inside the same machine?
Not necessarily, no. I mean, like once you validated it, you can, keep track of it, and you put it in a room, and you monitor that room, and it might be destroyed years later. But
You monitor the room and so on.
yes, so once you identify that this is okay, you keep track of it and all that. So what we propose is a new approach for word verification where we're still going to use some kind of physical assumptions, but we're trying to minimize them. Not to say we have a complicated machine that doesn't leak any information, but rather say assume much less about the components that we use and make the assumptions about things that are much simpler. And the secrecy property or certification property is proved by arguments that come from information theoretic cryptography. And the definition of security we use is the following. We say, okay, we have this game. Anna is the inspected party, and say Bob is the inspector, and they verify this object X. And we want to say that it satisfies completeness. If X is authentic, Bob will output accept. And soundness property, if X is not authentic, then with high probability, Bob will output reject. Yes?
What does authentic mean?
OK, so we'll make it more precise in a second.
If you don't know the design, how do you know?
Right, so in the previous thing, I think I didn't say it out loud, but like some properties that people said was like, if it contains more than 2 kilograms of plutonium, it's authentic, and there are other properties if it has this kind of mass or this kind of thing. So there were like some minimal properties that they're necessarily not completely,
Subset of the design.
some subset of the design that is possible to
So
reveal.
one candidate for authentic would just be, does it work?
I mean, you're not going to blow it up, right? Yes.
Okay, so I mean, you'll have to sort of pare down the...
Right, and in some sense, even if it works, what I mean, like how big, like you actually want, how you don't want like some sense for them to dismantle like some clunker from the 1950s and keep their high-tech new ones to themselves.
But isn't it just like, about the question of authenticity, isn't it going to be just like the usual zero-knowledge game? If there is authenticity, is whatever can be proved with information leak, and you are going to do it without information.
No, I'll show you in some sense. I'll show you soon. Like, authenticity will be, like in a second, we'll show what we mean to be authentic and will be much simpler. The zero-knowledge property is that you want to say that if you look at the total data that the inspector had learned, then that should be distributed independently from the actual object. So you shouldn't learn anything about the object. And in some variants, we're going to say it's going to have just small mutual information with so in some sense, statistically close to being independent from the object.
So this is not computational?
No, we are going to work information theoretic, yes. Okay, so now the talk outline. So first of all, there are two approaches for verifying, and what we work is not the attribute-based approach, which I kind of referred to before, but the template-based approach. And then I'll show like a cartoon version of our approach, and then I'll say actual proposal, how you implement it, and then give some analysis or a sketch of analysis of the second variant of the implementation.
It's more resembling statistical zero-knowledge.
Yes, or even, it's not like it resembles the one-time pad, but you'll see it. It's because it's like we use the physical properties, so it becomes a bit different, in some sense simpler. So, okay, so the two approaches that people have considered in the past for word verification are, one is the attribute-based approach, and this is kind of what I described before. Authentic will mean it has at least 2 kilograms of plutonium. And this.
It was 4 kilos.
Well, it should have at most maybe 4, but maybe at least you say okay, but it has at least 2. We know that it's some number between 2 and 4, and we don't know what it is. So we say if it has at least 2. And I guess one problem with that approach is if they actually needed 3 kilograms, then they can always take 1 kilogram out, and it will still pass the test. The second approach, which is the approach we are going to follow, is the template-based approach. And the idea is the following. You find a template warhead which you know to be authentic. So how do you know that it's authentic? You take a random deployed missile, you choose it, you go up there, you take out of the warhead, and this is your template. And you know it's authentic because Russians are very, they haven't, they're not going to deploy 90% of the missiles as fake missiles. It's not going to, that's the point of having nuclear missiles on the ready.
Protocol, right?
I mean,
security cameras in like Britain and things like
Yeah, I mean, we'll see. I think people don't think that this is a realistic concern that I mean, you'll actually see the activity they're going over and switching all their deployed missiles to fake ones. But
They would be vulnerable.
yes, and they would be vulnerable. So I mean, what you just not launch a nuclear attack. It's very simple. In this case.
Maybe it should be, instead of proving that you've destroyed missiles, you want to prove that you have missiles.
Yes, yes.
I mean, this is
Yes,
the reverse.
yeah, maybe they can choose a country to demonstrate this on. so,
That's how it's worked in the past.
yes,
How
yes.
to prove that.
So the idea of the template-based approach is that you are going to, so the test will be, you have the template, you know it's authentic, and the test will be that you're going to compare the object to the template. And this actually has advantages in the sense that now you can't still, you can't keep to yourself some of the mass, and you also can verify that not only they destroyed like a nuclear warhead, but they actually destroyed the nuclear warhead of that particular type that they declared that they're going to do. So this is actually an approach, regardless of zero knowledge, has some advantages over the previous one. And this is what we are going to use.
This would leak information that they only have one type, right?
No, I mean, the types actually they already declare, like they declare the various types that they have. So, and I guess when they have names.
This name is deployed here, here, and here.
Yes,
Okay.
yes, yes. And they say we are going to destroy 50 of that type, and I mean, somehow, I guess that's one reason why they have managed to maintain this fragile state is by being very open in some sense about what they have. So we are going to use to test that the template-based approach. And for the description, I describe it like a cartoon version of our approach. And for that, let's pretend for a second that the measurement is just taking an X-ray of the two warheads. So basically, like let's suppose that if you were doing the information barrier thing, you would take two X-rays, and you'd compare the films and see if they are basically have the same image or very, very close images. And if so, you'd output a green light, and if not, you'd output a red light. So let's say this is the.
Of course, one imagines X-rays are completely fogged in the presence of a nuclear weapon.
What?
X-rays are probably completely fogged in the presence of a nuclear weapon.
I'm not sure. Are they? I'm not sure.
Why? I mean, we're not using X-ray, I think.
Yeah, we're not using X-ray, but let's. Yes. So here is the cartoon version of our protocol. So Anna will prepare 100 pairs of films. Each pair of film will be exposed to an identical random image, and then she puts it in a sealed envelope. Then Bob comes, they do the inspection. Bob chooses 99 of the envelopes, he opens them and checks that they are valid films, they actually work and all that. And they have identical images.
Well, what does it mean, exposes each pair to identical? It's like a mask?
Mask, yes.
Okay, so a random mask which
Random
will
mask.
reveal half the features in some random location.
Yes, so yeah, you can say you took a picture of a random image, or you exposed if there were pixels, you expose each pixel to a random number, or random intensity, or. And what we took, take the two films from the unopened envelope that Bob didn't see, but now he's pretty confident that it's actually two valid films inside it, and two valid identical films inside it. And then you take X-ray of the template and the test warhead. And we take this template, and now Bob can compare the film. So if the warheads were different, now what you're going to get is a superposition of the image, of the random image, and the image of the warhead. So if they were different, the resulting films will differ. If they were identical, the resulting film will have the random image plus the warhead image. So it's supposed to be something roughly like an identical random image. Now, if the film acted like XOR, it would be exactly identical random. If not, and we'll talk about it a bit in the next slide, you kind of want the intensity of the random image to be much, much larger than the intensity of the superposition image, so the signal to noise ratio is very, very low.
So, but if the warhead was replaced just by an image of, just a face of a man or a face of a woman.
So in one case, you'll have the random image superpositioned with a warhead, and the other case, you'll have a random image superpositioned with the face. So it's going to be different.
No, I'm saying if forget missiles. I mean, suppose there were just two faces, and one was I don't know, face of a boy, and the other the face of a girl, or they were supposed to be the two faces of the same boy. Then if you just exclusive OR, then you'll see the same in both.
Yes, but even also if you add, right? So let's think of it as just a single number. So let's for a second think that it's just a single number. So both of them were initially exposed to the same number, random number R. And then you added in one of them you added x, and in the other you added x prime. If x equals x prime, they're the same. If x different from x prime, they're different. And if the magnitude of R is much, much larger, it's a random number much, much larger than x, then these are distributed, and if x was equal to x prime, then these will be identical numbers that are distributed kind of randomly. Right, so if you choose R from at random from a universe between 0 and capital N, and say x is a number, arbitrary number between 0 and some small n, let's say n is much, much smaller than, say, square root of capital N, or something like that, or epsilon n, actually, I think, for this thing. Yeah. Just say much, much smaller than n. Then if you were to see R plus x, and suppose x equals x prime, then you would not learn what x was given this thing. Right?
So you add up the two and you see the XOR of x.
Or yeah, let's say in this case the plus even, or the sum.
Or this is sum.
Yes. So suppose that R, capital R, was a number between 0 and capital N, and x is a small number between 0 and small n. And you learn these two numbers, R plus x and R plus x prime. And yes. And if x equals x prime, then they both cancel, and then you learn that they were the same. But what you actually, the information you learned about x is, say, at most some epsilon, like depending on this relation.
You repeat this now many times, like if you verify many warheads, then you might have a bit more information on that.
Right, so you would have to have this kind of small thing be dependent on how many times you're going to repeat it. Yes?
Why can't the machine just take two X-rays and then output the green light if they're the same?
Because we actually don't want a cage, right? We remove what we did is remove the iron cage. Now we don't have a machine that is inside the cage, so we actually give the inspector, the actual X-rays to compare himself. And we still claim that he didn't learn anything from that.
Wait, Anna is the inspected?
Yes. So Bob actually gets the X-rays, he can take them home. He gets the actual X-rays rather than just seeing a green light. So he actually compares it himself, so we remove the iron cage.
So does he know x or x prime as kind of the standard one?
So he doesn't know them because they are the secret design information. They are supposed to be equal. They're supposed to be the same object.
So Anna is the one who's trying to hide.
Yes.
So Bob is the one who takes the X-ray of the template.
Yes. So just Bob doesn't know. Bob can inspect. Can't see the envelope is sealed, so he didn't see the R before it got superimposed with.
Bob just needs to know that they're equal, and Anna is the one who wants to make sure that R is really right.
Yes. So it's in her interest to do it. Yes.
So each envelope has two random images that are
Identical.
to each other? Or
Yes, identical to each other.
envelopes?
No, identical to each other. Every envelope has independent image.
But I guess x will never be exactly equal to x prime.
Right.
So, but it does learn x minus x prime.
Yes. So we will do like x minus. Yeah, you will compare them, and if this difference is small enough.
So you learn something, that you learn about where there are differences in different warheads.
Yes, that's a good point. And in some sense, we we need to assume that like they are supposed to be identical, so we need to assume that the place where there are difference is like some kind of noise in some sense, and it's and indeed, but this is an issue that you have to think about. So let's talk about actual implementation.
Also, I mean, you have like the two identical X-rays that you're going to be, you know, the masks that you're going to be
Yes.
using, which are hidden.
Yes.
So how would you actually put those into a machine then? If they're, I mean, you know, someone's still taking them out.
So let's talk. We're not using X-rays, so let's talk what we are actually using.
I don't understand why it's zero knowledge. It's obvious that it's zero knowledge.
Like, I mean, in some sense, let's talk about like what we are actually using, maybe, then, and especially what I'm going to analyze. Then it will be more obvious that it's zero knowledge. In some sense, you would want to say, like, in this example, you want to say that this is distributed. Like, suppose x equals x prime, then this is distributed almost independently from x. You know, it's distributed. It's a uniform thing on the interval between x and n plus x. And the statistical distance of two things like that is like at most n over capital N.
What does the 99% use for? I mean?
This is just to make sure that that Anna didn't cheat. She didn't put like say the biggest risk that we have is that she puts films that actually don't work and they never they are just not sensitive to X-ray. So they will you will check them. They will have the same image because they will always give you the same image regardless of what. If you put here a coffee maker and a warhead, they would still put.
Why 99 and what not?
No, it just gives you like 90. So that guarantees Bob with 99% probability that is.
One you still need to use.
Yes.
Oh, I see.
Yes.
You don't use the 99.
Yes.
You use the 99.
Yes, you use one of them, and the others are just to check that she did okay. Okay, so let's talk about how we actually implement it. So we don't use X-ray, we use a neutron beam. So we have basically we shoot a neutron beam at the object, and this is just some cartoon, like some neutrons go kind of straight through, some get swallowed by the objects, and some get scattered and go to the sides. And we have like this array of detectors measuring these, measuring how many neutrons actually hit the other side. And yes, this is a picture of something like that, but it's not. We haven't built our actual setup yet. Yet. No, the Lex will be. Yes.
You're really going to build high-speed.
Yes. So. In the film, there are two versions. So one version which is a little bit more like film, this is called the bubble detector. This is some liquid which every time like a neutron hits it, it has some probability of creating a bubble. And then you put it in the microscope and you count how many bubbles there are there. So that's basically could be one mechanism where Anna will pre-shoot some neutrons at it before that. That would be like pre-exposing it to a random image, and then you put them in the machine. You can't really in the naked eye look and see how many things. You have to put it in a microscope and count it. And so that will be more like exactly like a film. Then a random image, basically you add to each bubble counter, you add a large random. You shoot at it a random number of neutrons. So you create a large random number of bubbles, and you need to keep low signal to noise ratio to make sure low mutual information with input. And in some sense, this is related to what Shachar was saying. You need to worry about you taking several measurements and maybe also measurements in nearby locations, or which you could kind of average over to reduce the noise. So you need to make sure that low means low enough that the low signal to noise is low enough that even after you averaged over several measurements, it's still low. And the second thing, which is easier, like you don't have to worry about this issue, so it's easier to analyze, is a digital detector that we have some counter, but we don't output. What we'll do there, we're not going to output the total count. The detector, we presume that we have some detector that only outputs one digit. It's simpler to think about binary digit of the total neutron count. So maybe it always outputs the 10th digit or the 5th digit from the right. of how many total Newton count, and it doesn't tell you in particular what's important. It doesn't tell you what's on the other side, like.
Hash function that's not sensitive to small numbers.
There are like these things that you actually, in some sense, you need to implement all these things in kind of physical world, and in some sense, you could say that maybe these things that get scattered around are a little bit like a hash function. The Newtons that go directly are more like a picture. The other ones kind of a little bit more sum up everything. So now random image, we basically say you initialize this digit, like it's a binary digit, you initialize it to 0 or 1 randomly. And so Anna initializes, and this is like basically just XORing with a random bit the end result. And then we get perfect secrecy like the one-time pad encryption. So I'm going to focus on this thing and going to describe it now more formally. So we want to have this protocol. We want to verify that two things are basically very similar, or let's say identical. So we have these two arrays of detector. Each detector has a state that is 1 bit, and it flips every time it counts k neutrons. Think of k as 2 to the I, where I is the digit that we were looking at. It flips its states to, from B to the negation of B. So that's basically this kind of counter. And what Anna does is chooses a random secret initial state, and she initializes both the detectors. Bob chooses a time. It actually turns out to be useful to make it a time random. So he chooses a random period of time, and he shoots the beam for t seconds on both objects. And he measures the results of these detectors. And it will set some threshold and will say if, at most, there were at most theta differences between the detectors, then it will say, OK, accept. Otherwise, it will say reject. And the theorem that we have is that under some specific reasonable assumptions, on what these things leak and what divergence creates in Newton count, then this thing satisfies our 3 properties.
It's not perfect completeness.
No, it's not perfect completeness. There's always going to be noise. And here is some kind of a proof by picture of how this thing looks like in the simulations that we ran. So this is the setup. And this is what happens when you simulate the diversion where you take 500 grams of plutonium out versus when we don't. So these are 2 objects that are identical. And in this object, you removed 500 of plutonium, and we look at what the total counts of these arrays. This is the total counts before we did this kind of just output 1 bit. You don't seem to see a lot of difference, but actually, if you were to focus on this side, actually the sides were the sides are where these kind of scattered neutrons arrive. I don't know if you noticed that I have here 2 lines coming out. This is because actually neutrons are created from the fissile material. So, and they typically go to the sides and enlarge the count on the sides. So you could actually, if you were to look at it closely, you could actually see it. So
you could mention maybe, the total amount of plutonium in this model is 4 kilograms. That's it's a shell, a spherical shell, about 1 centimeter thick. And we're removing roughly 1.5 millimeters from that shell. I mean, these are real, Monte Carlo simulations, but we're talking about 1.5 millimeter change in the geometry. So it's kind of smallish.
So yes, which is why we don't see it. So if you take this mod 2, you just output one particular bit, and you take this mod 2, you get this image. Which still might actually reveal some structure. In particular, it might reveal the distance between these 2 guys, which is also secret information. But then when you offset it with a random thing, then you basically get just random looking image. But if you were to compare these 2 images with these 2 images, then you'll see that like here, blue means that they are the same and green means that they are different. So you'll see that these guys are much more likely to be the same than these guys. So if you kind of queried here at, I don't know, 10 random locations, you would actually be able, you don't even have to put detectors in all this array. 10 random locations would be enough to distinguish between, or maybe 20 or something like that, you would, could distinguish between this situation and this situation.
So when you test the 99 pairs of random images, you only test that they are equal, or you somehow test that they are random?
I think you don't care that they are random because that's the interest of that's in the interest of the inspected party to make it random. So you don't care that they are random. In fact, you don't really care that they're equal. It's also some, in a sense, their interest to make them equal, especially if you just say that with probability 50%, you flip, so they don't know which one you're going to use on the test and which one you're going to template. What you really want to test is that they work. That if you shoot more neutrons at them, they're actually going to be sensitive to that. So that's really the test that you...
If you didn't test that they were equal, they could measure it themselves, measure the two themselves, take that difference and make one a random and the other the random plus the actual.
Right, but that's what I say. But if they don't know until the very end which one you're going to use on the template... Yeah, if it's symmetric, then yes. If it's with XOR, then you're right. If it's with the plus case, then it matters. But by the way, nothing that we said needed to use mod 2. We could have used mod 3. Yes, it's easy to check that they're equal. It's not a problem to check that they're equal, but in some sense, the real danger is that they don't work. That's the real way that they will make it fail, because like if you work mod 3, then say the thing wouldn't, then in some sense making them non-equal will be, and of course another thing is that, yes, making them non-equal will also, this kind of attack actually requires you to put the secret information on these pairs of films that the inspector gets to take home. But yeah, I mean, you could check that. It's very easy to check that. That's not. Yes. So that, but so this is kind of. And now let me say that, like, how the mathematical proof. So basically, the zero knowledge property is actually easy in this case. That's the easy property. It's like security of one-time pad, and you need to make a physical assumption that the detectors don't leak more than what they're supposed to do. But at least you're making a physical assumption about a very simple small detector rather than a huge complicated machine inside the box that, you know, does all this complicated logic. So it's more, it's a safer assumption. And of course, we have a version with the bubble detectors where the assumption seems even like cleaner. And you need to assume, which is related to what Shachar was saying, that either, you know, x equals to x prime, or they differ by some known noise distribution, or you have to do other tricks. So you subsample also, like you don't measure all the detectors, because in some sense you might get some information. If they do differ, x and x prime, you will not just learn that they're different, you will learn where they differ. So in some sense, if Anna is cheating and did use different x and x prime, she actually, we don't protect her secrecy in that case.
That's fine. Right?
Yes, that's fine, but what you have to worry about is if she was cheating inadvertently, and so, but these pixels are kind of very rough, so if the objects are very close to each other, you still shouldn't see the difference.
The inspector might kick
yes.
the objects.
Yes, you should be careful of the inspector, like starting to modify one of the objects, so they will be different because he will learn, he might learn something from the difference.
How do you know that they're actually shooting these neutron beams? Who's shooting the neutron beams?
So.
And how do you know that that's what they're actually doing?
Yes, so I guess that's one. You do need to make that assumption that this is this is a neutron beam and it is actually shooting neutron beams, and I guess the natural person to design this, to come up with the neutron beam is the inspector, but then you have to verify that they're not doing more and they're not somehow shooting some X-ray that then gets reflected off. Like the natural party to provide the detectors is the inspected party. So at least they have no interest in providing detectors that detect more than neutrons, or like, and the other party might provide the neutron beam.
Buy a machine from the IAEA.
So all you can do
Yes.
is the other detectors, the 99 detectors, you can actually run and shoot the neutron beam and test that you actually detect them.
Yes, you can check you can check that these things. Yeah, I mean, you can run, like, if the inspected party designed the neutron beam, but this still it's a more complicated machine. So you might want to make sure that it, you know that when you test it, it actually shot neutron beams. You don't know that maybe it has like a remote control. I mean, there is all.
Yeah, so question,
Yeah, I mean, we have not completely reduced physical assumptions. In some sense, we reduced them. We haven't eliminated them.
You reduce the problem of testing missiles for performing something to testing neutron guns.
Yes,
something like that.
yes, and yeah.
Maybe this is a safer device
Yes,
to test.
yes. I don't know. Maybe there is some natural device that shoots, if you're very paranoid, that shoots neutron beams. I don't know. Maybe you can plug a star and put it in a box.
You still have to authenticate the instrument.
Yes.
The common wisdom is that the inspected party and the host and the inspector develop the instrument together.
Yes.
So they're kind of familiar with the design, and then you may have critical components you put on the table, 10 of them, and you pick one of them for the experiment. The rest of them you can take home and disassemble and
Yes.
check that everything goes okay.
Yeah, I mean, with reducing physical assumption, we're not eliminating them in some sense.
But what I'm mainly worried about
Mm-hmm.
is how do you actually validate that, so you can like make up a device together, it's perfect, it does what it's supposed to do, and then say, okay, now you wait here, and I'll take the device into the missile silo and use it.
I don't know.
And how do you actually check that, so either they have to let you into their missile silo, in which case, how do they know that that's all you're doing?
They're both standing around the missile and doing it.
No, I think, yeah.
One party is taking this film, putting it in the device, and pushes the button.
Yeah, I think you're allowed to enter the missile silo. You're allowed to look at the missile. You're just not
Maybe
allowed
you have in
to.
your pocket some other measurement.
Yeah, so I guess you will be. I mean, you will be searched, and I mean, I don't know how it works. There's people have to come naked to the.
You're not measuring at the missile silo. I mean, one day
Yes.
you agree, today's Tuesday, we go to that missile silo out in, North Dakota and pick our golden, what is sometimes called the golden warhead. And that's the one we take home to, the lab, and we'll lock it into the room, and that's our template.
And then they bring the other things from their silos to the lab.
They have this whole room, a batch of warheads. They're identical to your golden warhead.
Right. And that's another question, which is how do you prevent them from just bringing the same warhead back over and over again? But I guess you're destroying it afterwards?
Yeah, now once it goes into the dismantlement facility, and that's relatively easy to do with, with containment surveillance, tags and seals, and basically at the very end, at the exit door, there will be some plutonium and HU coming out, and at the end of the day, you want, if you dismantled 100 weapons, you expect a certain amount of material, and there are people, you talk about mixing different types of warheads, so you won't actually learn how much material is in any specific type of warhead. I mean, you can add bells and whistles, but the real problem, and I think the broad agreement, is to initialize the process, to authenticate that you actually put something real in the beginning, and that's what we're focusing on. But we're open to ideas.
No, I'm just trying to understand what actually is happening where, and where does this fit into the broader scheme?
Well, there will be a dismantlement facility, and we know there are no tunnels, there are no extra doors, and we sit there. It has two doors, one at the beginning, one at the other end, and we just want to make sure whatever you bring to the first door is a real warhead, and we collect the rest of the stuff at the other end. And we're not allowed to go inside that facility while the warhead is being dismantled, but we can go back when everything's finished and can check that nothing's left over.
So So like the inspector monitors the entrances, nothing gets in and nothing gets out that he doesn't know about, and, but what happens inside, it's like and what we want is like at the door, when something gets in, it's...
Wouldn't it be simpler to just have a box, a big box that does this neutrino thing, it just compares the images, and it's designed by both parties?
So that's the information barrier. The problem is that it's a more complicated box. It does this thing, it has some logic inside, and
It's simpler because it does the same thing just without the randomness.
yeah, it's simpler, but
It measures classified information, and I've talked to kind of weapons designers and people who develop these instruments, and some of them
You don't
think
get to see the
you will
scans, you just get
Well,
to see if it...
but you will never be, but you can't be sure that there's no backdoor, that there may be this secret transmitter in there that actually does send out the information. That's what they're worried about.
But don't you have the same worries when you
Yeah,
build this
so
nuclear, I mean, this
transmitter and this
this
neutrino.
neutron beam?
yeah, you try to make your worries about simpler components, rather about making your worries about certifying the whole system as a whole, make your worries about a smaller component of the system that you actually see in action. It's about just about making assumptions about simpler objects than that have well-defined things that rather than the complete system that makes the measurements and all that. So I mean, the more complicated the machine, the less. I mean, especially if it was a computer sitting there inside there and doing the logic, the less.
It's the same machine, just without the randomness. It's exactly the same machine.
No, I mean, it was a computer that reads these things.
It involves something that takes the output and compares it instead
Yes.
of an output that takes it, stores it with a random string and then compares it.
But at some point in time, you did a measurement of an atom bomb. So, and they don't want this to happen.
No, but here you do it. You also do it.
No, there is never a single place where you
They have
see a
20
picture of
detectors.
Oh yeah, and also like the detectors were never actually measured because they had this, preloaded.
There's nothing we have to do after the measurement. Maybe we initialize it before, but the data that is measured, we don't have to post-process the data, and that's the critical difference.
There's
And if
no
we
place in the system where the memory gets to see the actual...
right.
Yes.
I guess the detectors you can buy off the shelf or something. And
Yes.
so there's no backdoor.
But yeah, but in any case, like I said, we eliminate physical assumptions. So in some sense, in a qualitative sense, you always have some kind of physical assumption. You're just trying to use crypto to kind of
Get a clear statement
Yes.
about the assumptions that are allowed.
Yes. So one yes. So the assumption is, let's say, the detectors work, and the neutron beams shoots neutron beams and doesn't take X-ray pictures of the thing. So, or in some sense, this is like no other data than D and D prime is leaked. That's an assumption. And in completeness and soundness basically follow from the following kind of lemma. So you want to say that if think of these as two particular measurements of the two objects, and you want to say that the probability that they differ modulo 2, and the probability, what is delta? I don't know if you recall, but Bob chose the time that is going to measure at random between 0 and time t0. And the number of neutrons that you're going to see is basically going to be, if you were to measure t0 time, you were going to see x. When you chose it randomly, you're going to see delta x in one of the objects and delta x prime in the other object. And you want to say that the probability that these two things are going to differ, and then you divide by some scaling factor, and you take modulo 2, you chop it down, and you take modulo 2, and you want to say that the probability that they differ is related to the difference between x and x prime. So in particular, I want to say that if x minus x prime is much smaller than k, then they will differ with very low probability. If x minus x prime is much larger than k, then will differ with kind of probability actually pretty close to half, which kind of when you work modulo 2 is what you expect. And this is very simple lemma, but it's the only lemma I have here, so you might want to try to make sure that at least this is understood. So let's prove it. So let's prove this inequality. So one thing, how do you prove this inequality? You say, okay, suppose that these two things were equal, then if you were to, if they were equal for some delta, then if you were to add to that delta k divided by x minus x prime, then these things are actually going to then you're actually going to make a difference of then they're actually going to be distinct. So they are going to be like one off.
So I'm not understanding.
Mm-hmm.
So it seems okay. Seems that this formula,
Mm-hmm.
you're sort of assuming that the number of recorded neutron collisions is exactly proportional to the number of beams and the time for the beam and sort of the density of the material.
I don't know. Let's not the other thing. Let's say it's proportional to the number. Yeah, I've assumed that if you shoot twice, you're going to get twice the number of neutrons. If you shoot for twice as long, you're going to get twice the number of neutrons that you got.
And it's going to reflect how something about the
It's going to be some complicated function of the number of neutrons you're going to see at a particular detector is going to be some complicated function of the object.
But okay, so but won't it be like more like a Poisson distribution, where?
Yeah, that should be the expectation, right? I mean, these will be like
the expectations, but then the actual number is going to be a Poisson distribution.
Yes.
With these expectations.
Yes, the actual number is going to be so. Yeah, so this is like a simplified.
And you're going to get two independent samples.
Yes.
So you're not necessarily going to match even if they're identical.
Yes, but I mean, if they're going to be very close in expectation, you expect to have actually the same integer most of the time, and yeah,
Well,
also with.
That's not clear, right? So you have to be. It's going to be somewhat delicate if you have like a Poisson distribution with a certain expectation, but you're taking the number mod
Yes.
a small number that may well the actual value may well be lost.
Yes, so yeah, that's actually a good point. So you actually need to make to measure long enough that the noise that you expect from Poisson will be, say, negligible compared to that value k that you.
That's what I'm actually worried that if you do it too long, then.
But you can output like a more significant bit or something out of the counters, right?
But so how big is k? Because you need k to be small for the zero knowledge.
No, k doesn't need to be. The zero knowledge property is independent of what you choose k. Like the zero knowledge was perfect regardless of what you chose k. K is just a scaling factor of what digit are you outputting. So you choose you can choose k as much as you want. It doesn't harm the zero knowledge property. So roughly speaking, you would think that x minus x prime, they are going to be like x and x prime are going to be, say, maybe 1% different in the good case and 10% different in the bad case. Yeah. And we're gonna make them big enough so that the Poisson thing, like the noise, is.
K is going to be about 2% of
Yes.
the range or something?
Yes, exactly. And if I haven't made a mistake in this proof, which I hope I didn't, then if they're equal here and you add this amount, then suddenly the mod will not be equal because you'll make them off by 1. And
you're just talking about the probability
right.
of an interval of a certain length landing between them or including them both.
Yes. Yeah, I mean.
Outside. That's the parity is just about that. So
yes.
One question is about you have some distance between them and you
yes.
have an interval. And
yes.
What you're interested in is what you want to say is if they are close, then most of the time. So unless
right.
the interval has just one endpoint of each function between them,
yes.
low probability.
Yeah, I mean
parity will differ. On the other hand, if they are far apart,
Yes, I mean, I think that's basically exactly what you say. Like if like in this example, like say in the second line, say basically you have like you basically have a uniform distribution of over some interval, and let's say they are the integer. These are the integer things, and in one example, so in one example you have the uniform distribution of an interval, and you have two things that are either very small, like only epsilon distance apart, and then it's kind of obvious that they are going to be rounded down, like with 1 minus epsilon probability to the same thing, or they are actually more than one distance apart, or like 2 or 3 distance apart, and then like half the time they're going to be.
You'd say let R be the difference between x and x.
Yes.
Prime, and then you're saying like draw, look at R times the time mod 2k.
Mm-hmm.
And now you're seeing, whether that's in how much of the time it's in the first half of the interval versus the second half of the interval.
Yeah, I think this is basically it. You could write like you could actually I mean if in this kind of picture you could actually show exactly the places in the interval where they're actually going to have the same modulo, and it's going to be. So if it's larger, then it's going to be roughly half the time, and if it's smaller, it's going to be, epsilon of the time. This is very nothing really going on here, and that's basically, and then what you really need to show, and that's basically that part we only do with simulations, is to actually show that we don't have a theorem about that under some physical model that if you do some significant diversion of the If you do some significant diversion of this, you take some thing out, you are actually going to see a difference in measurements, say a 10% difference in measurements in significant fraction of the detector. And it might not be all detectors, it might be detectors in particular region and all that. But that part we don't have like a theorem about it in some sense. And you might actually need to use different detectors in different regions and different energy levels of neutrons and different numbers k. But at the end of the day, you will always have this kind of phenomena. You want to say that if they're close, the mod will agree. If they're far, the mod will disagree.
If you're taking so few bits out of the image, maybe there's some completely different object that just has the same.
Yeah, one thing that you are going to do is you're going to decide which bits to take after the object is already in a box. So they can the bits you take not necessarily secret, but they are selected after the object had been already prepared. So that's actually important. So one reason is something related to what you said. Like in some sense, if you measure things very, very, very finely, and you could have this kind of phenomena where, suppose you had, suppose this was your object. This is the template object, and the test object was kind of 1 millimeter off. So it's like this. Now you are going to see the differences. You're going to see. So you somehow you don't want to avoid these kind of things. So you don't want to be too fine a scale.
Like what you're trying to do then is you have different metrics for closeness.
Yeah, but this is actually revealing something for you. This is actually.
So then you're saying your Hamming metric is the wrong metric.
I mean.
You would need a different
function
that would be good for that.
No, I mean, this is actually good. Like in some sense, this will pass the test. There are a few places where it differs. The only thing is that the guy didn't cheat, but you learned from the places where they differ what you did. So in that case, actually, you could still do some things. Like you could shuffle. You could say before you actually measure the detectors, you put them in a bag and shuffle them, so you don't know which positions you looked at. So.
Okay, not clear that you would get, if you're off by, if you're off by more than the, if you have like these different sort of random pixels that you start with, right? So you have on the film before the process starts some bubbles.
Yes.
Okay. So, and these bubbles are sort of in discrete regions.
Yes.
If the contents are shifted by more than the distance between these bubbles or something that you start with, then things are just not going to line up.
Yes.
And so your counts are going to be totally off.
I mean, if they're completely shifted, but if they're like,
Shifted by just even,
but if the object is itself somewhat continuous, like the object itself has the property that it's somewhat continuous, like you would, so you kind of will see the contours of the objects if it's shifted very slightly, but I mean, maybe I'm not very clear. Like one of the things you actually, the system is designed, I mean, and you can have like other methods. So like I said, you could shuffle the detectors before actually looking at them, but suppose you don't do that, then the system is kind of designed to tell you where the differences are. And that's okay because there's supposed to be no differences or just random noise differences if the objects are truly identical. But if the differences are systematic, then so you would learn something from that. So you have to kind of think about this and design it at a sufficiently low resolution. So.
But it's also a problem for completeness.
Yeah, it might be also a problem of completeness, but it might become a problem for zero knowledge before it becomes a problem for completeness. So you have to, in some sense, zero knowledge is more delicate property because in some sense you could always verify completeness in the field by shooting the same object twice and see that you actually get a match. So you could. So completeness is less delicate property. Zero knowledge is a property is more delicate. So.
I mean, okay. So say you have the same general outline. So the question is how close in, so you have like one component here and one component there, and they have, I don't know how nuclear bombs are made, right? So but the question is
That
how.
is the first time in a lecture here that Russell doesn't know.
Or maybe the first time I ever did it. But,
it's the last time because by next lecture he will know.
So the question is, you have two different devices, they're following the same pattern, how closely do they actually match up? So it seems like if there are two main components but they're not exactly in the same relationship with each other, that you could end up having very wide divergence.
Right. So in some sense you have to allow for
different, manufacturing changes are different from running it with the same device twice.
Yeah, I mean, you have to allow for manufacturing divergence. I think, fortunately, at least, it seems that, I don't know, maybe Alex knows more, it seems that people design these things with care, so they try, it's very careful design that they've, so they try not to deviate too much between these two things, so that's why you can assume that these things are more or less identical. But obviously, like, there is error, both error, the Poisson error that you mentioned, and design error. And part of the reason why we're going to, we're running simulations, but we're also actually going to run experiments, not with real nuclear weapons, but with kind of mock nuclear weapons, is also to understand. There's also another error that comes from the room, neutrons getting reflected from the room that you're in, and